So we are still on fluid dynamics problem. So let's try to read what is given us. A velocity potential generated by a helicopter blade represented here. Let me say we have a helicopter here, then there's a blade. See our helicopter, and A is pushing in like that, like that, like that. See, that's actually the air that helped the helicopter to rise. So the flow in the vicinity of stagnation point just here. Okay, so that the pressure gradient along the surface can be represented. So once how pressure is changing as I move through the surface. Then they gave us the answer, so we're supposed to find if this answer is true, if it is true. So for our velocity potential, we have a beautiful formula that we can use that says U is equals to partial of that all over in X, and then V that. So these are our building blocks, right? And then from here we can find VU and V, but let me just be interested in this. So I think we're also going to take advantage of our Navy stock equation for the first time in a very long time. So we're going to dV dt, that is pressure. Oh no, that's not pressure, that density, because this formula is the same as saying mass times acceleration. Remember, from Newton's second law, is equals to change in pressure plus mu, then that's that Laplace time u plus some external force. Let me call it G. Let me just call it force anyway, because that's my external. So this is for my these two are my internal forces. This one is pressure gradient, this one is viscosity friction, this one could be gravity or whoever, right? So this part is my MA. So this is literally F net is equal to all the forces. Think in your Newton's second law. So these things are vectors. Also, I think it's worth noting. So interested in finding the pressure gradient in X direction. So if I use a chain rule here, I would have dV d2 plus u dV dx plus v. 2 dimension I think would be enough for me. I don't have to go anything above this. These are vectors dy, right? Actually, I don't know what I'm doing. I'm just writing everything that I need. Hopefully I'll end up with what I want. This is also a vector, I think. So I think from this guy we can assume a couple of things to make our work. We can assume that it's ideal, so there is no mu, so this thing will go to 0, and we don't consider our forces external. This one is going to 0, so end up having this beautiful thing. This is a vector. This guy will have partial of p in x and p and all of that, but we're only interested in partial of p in x. That's what we like. But here this is a v, right? So v is literally 3 dimension. You want to limit it to 1 dimension, so we'll be only left with u here. So also assuming this thing is steady, we have to get rid to this time. So steady means there's no change as time changes. So now we can have density u du dx, that partially, plus v partially also du dy is equals to whatever that we're interested in. Right, so I think the only thing that's standing on our way now is finding v, and for us I brought back this equation that we said are going to be on our toolbox to start everything in here. So I think can say u is equals to partial of whatever that in terms of okay, let me put whatever I'm trying to derive so that we can remember it here, x squared plus y squared. So if I'm deriving that in terms of x, only this guy will be, I take out the constant, only that guy will be influenced, become 2x, and then this one will become nothing. Then my v, deriving this in terms of y now, so take the common factor, this guy will go down, I'll have having 2 y. So these are what we're looking for. Then if we derive them, they want to take u in terms of x. Okay, let me write it here, du in terms of x, that's our guy we're interested in right now. In terms of x is going to be, then we'll get negative k, only the 2 would remain. But what if we try it du in terms of y? I think we need that here. It's going to be the same guy in terms of y. There's no y there, so it's becoming 0. Okay, that's nice. So we have all the tools. We don't need this guy now. These are our tools. Let's go back to saying our partial p in terms of x is going to equal to density. We know what is u. U is that negative k 2x. Du in terms of x, it's going to be negative 2k plus what is v. We're not really interested what is v because we're multiplying by this, and this is, we already know this is 0, so we can just add 0 here. I don't have to do all of that math stuff. So this is going to equal to that. I think here we'll end up having 4kx. Did I miss anything? I think there are 2 k's here squared to become positive, and then they proposed that our answer should look like this. So it should be a constant and some x, where a is a constant and k is also a constant. That means this is what you can call your a if they asked what is value of a. So yes, we have proved that pressure gradient along x behave linearly, where this is that. So thank you.